Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up Chapter 5 from your textbook by taking a look at Section 5.3. This Section 5.3 basically introduces you guys to a way of taking a basis for a given vector space and converting that basis into an orthogonal basis. And the reason that we're going to talk about this is because, as you guys saw in the previous video, if you have an orthogonal basis, finding the component representations of a given vector relative to that orthogonal basis is pretty simple using those different projections. So the idea is, sort of putting all this together, is that we know how to find normal bases for a given vector space. If we then had a process to convert a normal basis into an orthogonal basis, then we could make use of that projection idea to actually come up with the component representations of a vector relative to that orthogonal basis without ever having to solve any systems of equations. Now, again, because our course is not a full class in linear algebra, we're mostly just going to take a look at this as sort of an interesting topic and then sort of leave it at that. If you guys ever take a full class in linear algebra, you'll see that understanding things from an orthogonal basis perspective is something that is very, very common in linear algebra in general. But to start off with, before we talk about the process of converting a normal basis into an orthogonal basis, we have a very small, I should be using the laser pointer there, a small little theorem. It's basically actually should be considered a lemma. It basically sets up the process that we're going to be talking about on the next page. But let's go ahead and talk about this theorem first. So what this theorem says is let's let V1 and V2 be vectors in some inner product space V. Then if you let W1 be equivalent to the first vector, and you let W2 be equivalent to the second vector minus the projection of the second vector onto the first, then these are guaranteed to be orthogonal. Now, we're going to prove this in just a moment. It turns out to have a very sort of quick and easy proof. But before I get to that proof, I want to talk a little bit about exactly what this is saying. What this is basically saying is, if you remove, in this case from V2, the projection of V2 onto W1, basically you're removing the projection, then you're guaranteeing, because you remove the projection, well, you're guaranteeing that this guy will be orthogonal onto this. I want to draw you guys just a little sort of basic sort of picture here. Let's imagine we're actually working with like geometric vectors, right? And let's sort of imagine maybe this vector here, that's V1. And then let's imagine that this guy here is V2. Now, as you guys can see by my little drawing here, these guys are certainly not orthogonal. What this is saying is, okay, let's go ahead and let W1 be exactly the same as V1. So that is also going to be W1. And then we're going to sort of create the projection of V2 onto W1. So what that would look like is if you project this guy down here, since I made this guy nice and easy and horizontal, the projection would literally just come down on here. So the projection would be sort of this right here. And that red one there, that would be the projection of V2 onto W1. Okay, now we're going to remove that projection from V2. So we're going to subtract this from V2. Remember, if you remember geometrically, how do you subtract a vector? Well, you sort of go from the endpoint and then go in reverse. So if we did that, right, if we sort of take this guy and we reverse it from that endpoint there, well, then the resultant vector from the origin to that new point, that would be W2. So W2 is that guy. Now, what do we notice about W1 and W2? Well, W1 is horizontal, and now W2 is vertical, so they would be orthogonal. And that's all this theorem is basically saying, but in general, not just for 2D vectors with the standard inner product, but for any inner product space. If you remove the projection of one vector along another from the original vector, then you guarantee you have an orthogonal pair. So let's go ahead and prove that. So what we need to show is we need to show that the inner product of W1 and W2 is equal to 0. So let's do our proof here. W1, W2. What does that inner product look like here? Well, that inner product, we know what W1 is and we know what W2 is. So this would be the inner product of V1 with V2 minus the projection of V2 onto W1. Okay. Now we know that W1 is really just V1, so let's go ahead and just rewrite this in terms of all V's. So V1, V2 minus P of V2 onto V1. Okay. Now, to do this, right, we know what this projection looks like. So we can say that this is the same as V1, V2 minus the inner product of V2 with V1 divided by the inner product of V1 with V1 times vector V1. Okay. Now, one of the properties we know for inner products is that you can split apart an addition in one component. So we can treat this as the inner product of V1 with V2 plus the inner product of V1 with negative V2 V1 inner product over V1 V1 inner product times V1. Okay. Now another thing we know is that this right here, negative inner product V2 with V1 over inner product V1 V1, this is all just some constant. So one of the properties of inner products is we can pull that out. So this is now inner product V1 V2. I guess it'll become a subtraction, so we can just say minus V2 V1 inner product over V1 V1 inner product. And what's going to remain in here? Well, just V1 with V1. V1 V1. Okay, now notice inner product V1 V1, inner product V1 V1, those are just scalars, and they're the same scalar, so they cancel out. So we get V1 with V2 minus V2 with V1. Okay, what do we know about this though? Well, we know that the inner product is commutative, so we can flip around the order of that. So we can say this is V1 V2 inner product minus inner product V1 V2, and that, of course, is 0. Check. So we've now proven in general, if you have a vector and another vector minus the projection along that first vector, those are guaranteed to be orthogonal. Now we're going to talk about how you can do this not just for a single pair of vectors, but for an entire basis of vectors. And that's what's called the Gramschmidt process. So let's go ahead and take a look at that. So the Gramschmidt process basically says the following. You have V in inner product space, and you have an actual just normal basis for V. So V1 through Vn is a basis for V. Then this Gramschmidt process allows you to convert this V1 to Vn into an orthogonal basis, W1 through Wn. Notice that if this guy has n vectors, then this guy has to have n vectors because the dimension has to be the same, right? It's a basis, so the number of vectors has to be the same. How do you actually build this orthogonal set? Well, you start by letting W1 just be equivalent to V1. Then W2 is V2, but you remove the projection along W1. From what we just proved in that previous theorem, that guarantees that these two will be orthogonal. For W3, you start with V3, the third thing in the original basis. Then you remove the projection along W1. That'll ensure that this guy is orthogonal with that guy. Then you also take V3 and you subtract not only that, but also V3 projected along W2, which will ensure that this guy and this guy is orthogonal. You rinse and repeat until you get to Wn, which will be Vn, the last guy in the original basis, minus all of the projections onto all of the previous W's. From our previous theorem, this guy is guaranteed to be orthogonal to every one of the previous ones, meaning this entire set is an orthogonal set. It has the same number of vectors, so it's going to be an orthogonal basis, and this shows us how we can convert from any normal basis into an orthogonal basis. Now, we could go through a pretty formal proof of using the previous theorem and showing why every one of these is guaranteed to be orthogonal to every other one. I'm not going to bother with that because, again, this is not the sort of main focus of our class. This is just a nice extension of the idea of a basis to an orthogonal basis and how to convert between those. So instead, we're going to jump right in and just look at a couple examples of using this process to build orthogonal bases. So let's go ahead and take a look at that. So the first example we're going to consider is we've got the inner product space R3 with the standard inner product, just the dot product. So we're being told that this set of vectors, 1, 1, 1, 1, 4, 4, and 1, 1, 2, is a basis for this inner product space. This guy, though, is clearly not or an orthogonal basis. Just check the first two. Inner product of 1, 1, 1 with 1, 4, 4. Well, that should give you 1 plus 4 plus 4, which sounds like 9. So that's not an orthogonal basis. So we're going to use the Gramschmidt process to form an orthogonal basis. And then once we have our orthogonal basis, we'll normalize it to create an orthonormal basis. So let's go ahead and see how to do that. So for convenience, we'll call this guy V1, V2, and V3. How do we find these things then? Well, we say W1 is just going to be equal to V1, which is just going to be 1, 1, 1. So our first element in our orthogonal basis is going to be the same as the first element in our original basis. Now for W2, we're going to start with V2, and we're going to subtract the projection of V2 on to W1. V2 is 1, 4, 4, and we're going to subtract the inner product then of 1, 4, 4 with W1, which is 1, 1, 1, divided by the inner product of 1, 1, 1 with itself, 1, 1, 1. That will be our scalar amount, and then we will be multiplying that onto the vector 1, 1, 1, which is the W1 vector. Okay, so what that then gives us is that gives us 1, 4, 4 minus this inner product here. We did that when we were just mentioning that the original set was not orthogonal. It's 1 plus 4 plus 4. That sounds like 9. And then down here we have 1, 1, 1. So that sounds like 3 times 1, 1, 1. Okay, that means we get 1, 4, 4 minus 3, 3, 3, which sounds like we get minus 2, 1, 1. So our second element of our orthogonal basis is going to be minus 2, 1, 1. Let's just check real quick. Is this guy really orthogonal to this? Well, negative 2, 1, 1, that does sum up to 0, so this guy is definitely orthogonal to this guy. Now we're going to go ahead and build ourselves W3. W3 is going to be V3 minus the projection of V3 onto W1 minus the projection of V3 onto W2. This part is going to assure that W3 is orthogonal to this, and by subtracting this, it'll ensure that W3 is orthogonal to this. So let's go ahead and take a look at what that's going to be. W3 is going to be V3. V3 was 1, 1, 2. So we're going to start with 1, 1, 2. Then we're going to subtract the inner product of 1, 1, 2 with W1. W1 was 1, 1, 1. So 1, 1, 1. Divided by the inner product of 1, 1, 1 with itself, 1, 1, 1. And then times W1, which is 1, 1, 1. Then we're going to subtract the projection of V3 onto W2, which is this guy here. So we'll need to do the inner product of 1, 1, 2 with minus 2, 1, 1. And then divide that by the inner product of minus 2, 1, 1 with minus 2, 1, 1 times the vector minus 2, 1, 1, which is W2. Okay, so let's see what we get there. W3 then is going to be 1, 1, 2 minus, up here it looks like we're going to get 1, 2, and then 2 again, so that's 4 overall. And then we already did this inner product. This came out as 3 there, times 1, 1, 1. And then we're going to subtract here. Looks like we'll get negative 2, and then 2 and 1, so it looks like we'll just get a 1 up top. And then down here, looks like we should get 4, 5, and then 6. So minus 1, 6 times minus 2, 1, 1. Okay, so W3, looks like everything's going to be in denominator of 6, so I guess I'll just get ready for that. 6 over 6, 6 over 6, 12 over 6, minus 8 over 6, 8 over 6, 8 over 6, minus negative 2, 6, 1, 6, 1, 6. Putting all that together, W3 looks like it's supposed to be 6 minus 8 plus 2. So that sounds like 0. And then 6 minus 8, negative 2 plus 1, or minus 1. So that sounds like, what, negative 3 over 6. And then 12 minus 8, that's 4, minus another one, 3 over 6. So it looks like W3 is supposed to be 0, negative 1/2, 1/2. Let's confirm that this guy is orthogonal with W2 and W1. This guy with W2, which was right here, that's going to give us 0, negative 1/2, positive 1/2. That is orthogonal. With 1, 1, 1, it's going to give us 0, negative 1/2, 1/2. Definitely orthogonal. So that is an orthogonal basis. So this set, 1, 1, 1, then negative 2, 1, 1, and then 0, negative 1/2, 1/2 is an orthogonal basis for R3, right? And we built that using this Gramschmidt process. So There we go. That shows you guys an example of how to convert from a normal basis, just a standard basis, into an orthogonal basis. All right, now I'm going to grab this guy real quick, and before we move on to the next page, we'll copy that. Let's go ahead and see how to normalize this. So for part B here, zoom in a little bit. It seemed like I caught a little part of this guy here. Okay, so for part B, we want to normalize this set. All right, so this is an orthogonal basis. We'd like to make it a orthonormal basis. So all we need to do is calculate the magnitude of each of these. So let's figure out the norm of 1, 1, 1, which is going to be the square root of the inner product of 1, 1, 1 with itself, 1, 1, 1. Well, that's just going to come out as the square root of 3. The norm of negative 2, 1, 1 is just going to be the square root of the inner product of negative 2, 1, 1 with itself, negative 2, 1, 1. And that looks like it's going to be square root of 6. And then the norm of 0, negative 1 half, 1 half is going to be the square root of the inner product of 0, negative 1 half, 1 half with itself, 0, negative 1 half, 1 half. Okay, and if we do that, looks like we'll get a quarter and another quarter, and add those up, we'll get the square root of 1 half, which is 1 over root 2. So now we divide each of these guys by their individual magnitudes. So our orthonormal basis, okay, we get to divide all these guys by root 3. So it looks like the first vector should be 1 over root 3, 1 over root 3, 1 over root 3. For this guy, we have to divide by root 6. So it looks like it should be negative 2 over root 6, 1 over root 6, 1 over root 6. And then for this guy, we need to divide by 1 over root 2, which basically means multiply by root 2. So we get 0, negative root 2 over 2, root 2 over 2. Now, if you guys want to check, you can see that this is an orthonormal basis. Each of these guys will now be guaranteed to have norm 1. And, of course, they'll still be orthogonal because each of these are just scalar multiples of these. For checking that they're actually they're all unit vectors, just think about this guy. Inner product with himself, you're going to get 1/3 plus 1/3 plus 1/3, which is going to be 1, definitely an orthonormal basis now. So notice that the Gramschmidt process does most of the hard work. It converts the basis into an orthogonal basis. Normalizing is just simply dividing by the norm. So this part is the very easy part. All right, let's take a look at one more example of using the Gramschmidt process to build ourselves an orthogonal basis. So we're going to consider the inner product space S being the symmetric matrices, the matrices that have the property that their transpose is equal to themselves, and they're 2 by 2 matrices. So this is actually not a standard vector space. It's a subspace of M2 of R, but by itself, it can be thought about as an inner product space with the standard inner product that we've been using for matrices, which is the trace of the transpose times the other matrix. So we're being told that this set of vectors here, 1, 1, 1, 1, 1, 0, 0, minus 1, and 0, 1, 1, 0, forms a basis for S. Now you might be saying, well, there's only 3 vectors here. Isn't this dimension 4? Well, this is dimension 4, but when we actually studied the subspace of the symmetric matrices, it actually is a 3-dimensional subspace of M2 of R, because this does put some limitations on it. So this is actually a basis not for M2 of R, but just for this subspace of symmetric matrices. So we're going to use our Gramschmidt process to form an orthogonal basis for S. So once again, we'll name this guy V1, this guy V2, and this guy V3. Then W1 is going to be equal to V1, so we will still use 1, 1, 1, 1 as our first element. W2 then is going to be V2 minus the projection of V2 onto W1. That means we're going to be doing 1, 0, 0, minus 1 minus the inner product of V2 and W1. So the inner product of 1, 0, 0, minus 1 along with 1, 1, 1, 1 divided by the inner product of 1, 1, 1, 1 with 1, 1, 1, 1. and then times the vector 1, 1, 1, 1. Of course, by vector we mean matrix in this case, but we're treating that as the vectors of this special subspace. So let's go ahead and see what that gives us. That gives us 1, 0, 0, minus 1. Minus, okay, to do this, we'll have to do the trace of the product. We got to do the transpose of this guy. So 1, 0, 0, minus 1 times 1, 1, 1, 1. And then down here, we have to do the trace of the transpose of this, which is still going to be 1, 1, 1, 1, times 1, 1, 1, 1. And then the result of that times the matrix 1, 1, 1, 1. Okay, so looks like that should be 1, 0, 0, minus 1. Minus, okay, let's actually go ahead and do that product. The trace, first row, first column, looks like we're going to get 1, then something we don't care about, something we don't care about. This guy times this guy is going to give us negative 1. Now at this point, I'm just going to save ourselves a little bit of work. We're going to notice that the trace is going to be 0 here. So it doesn't really matter what this is, doesn't matter what that. So this will just say whatever. And this guy is going to be 1, 1, 1, 1. Now this trace here is going to be 0. So this is going to come out as 1, 0, 0, minus 1. So that tells us that W2 is actually supposed to be V2. Well, let's go back and check. That's basically claiming that this V1 and V2 are already orthogonal. And that's what we just showed by doing this inner product up top. We were going to get a trace of 0, which shows that those two are orthogonal. So these two are already orthogonal. So if we're forming an orthogonal basis, we can just keep these two as is. Now we might need to modify V3, though, to make sure it's orthogonal to these guys. So let's go ahead and do that. So for W3, we're going to be taking V3 and subtracting the projection of V3 onto W1 minus the projection of V3 onto W2. So that means W3 is going to be V3, which looks like it's 1, 0, 1, 1, 0. So 0, 1, 1, 0. Minus this projection, so 0, 1, 1, 0, along with 1, 1, 1, divided by the inner product of 1, 1, 1, 1 with 1, 1, 1, 1 times the matrix 1, 1, 1, 1 minus, then we got to project onto W2, which is this guy here. So minus 0, 1, 1, 0 along with 1, 0, 0, minus 1 divided by the inner product of 1, 0, 0, minus 1 along with 1, 0, 0, minus 1. Okay, and then of course that'll be times 1, 0, 0, minus 1, which is our W2. Okay, so be a little bit messy, but we can go ahead and do that. So this tells us that W3 is going to be 0, 1, 1, 0 minus the trace of the product where we take 0, 1, 1, 0 and then multiply by 1, 1, 1, 1 divided by the trace of when we take the product 1, 1, 1, 1 with 1, 1, 1, 1 times 1, 1, 1, 1. Okay. Yep, that's looking good. Just making sure we didn't miss anything there. Yep, okay, all good. So we've got that, and then minus the trace of this guy, 0, 1, 1, 0, times the other guy, 1, 0, 0, minus 1, divided by the trace of 1, 0, 0, minus 1 times itself, 1, 0, 0, minus 1, times this guy, 1, 0, 0, minus 1. Okay. So we've got all that, so we can say that W3 then is 0, 1, 1, 0 minus the trace of, well, we only care about this guy times this guy, which looks like it's going to be 1 something, something, and then this times this is going to be 1, divided down here by the trace of this times this, so that looks like it's going to be 2 something, something, 2. times 1, 1, 1, 1, minus, up here, trace this guy times this guy. Looks like that's going to be 0, something, something, and then this guy times this guy. Oh, that's going to be 0. So in that way, we can already see that the trace of that is going to be 0, so we don't really care about that, and we don't care about that. So we get W3 here is going to be 0, 1, 1, 0, minus this trace, which is going to be 2 over the other trace, which is 4, and 1, 1, 1, 1. All right, this whole thing drops out, telling us that actually W3, or this guy, sorry, V3, was already orthogonal to W2, so we just need to remove the component that relates to W1. And if we do that, it looks like we should get minus 1/2, 1/2, 1/2, minus 1/2. So our orthogonal basis here is supposed to be the vectors 1, 1, 1, 1, W2, which turned out to be 1, 0, 0, minus 1, and minus 1/2, 1/2, 1/2, minus 1/2. And there we go. That is supposed to be our orthogonal basis for our set of symmetric 2x2 matrices. If you guys want, on your own, you can confirm that the inner product of these two, the inner product of these two, and the inner product of these two are all 0. You should also sort of believe that this would form a basis for the symmetric matrices, because you will notice that all of these are indeed symmetric matrices. So that pretty much wraps up our discussion of the Gramschmidt process. Gramschmidt process is basically just a computational process that allows us to transition from a normal basis into an orthogonal basis. In our next video, we'll be moving away from talking about inner products and begin our discussion of transformations, basically mappings or functions from one vector space to another.